Hello everyone, NodLabs here. Today we're going to be making this sort of wall climbing system in the Godot Game Engine, version 3.3.1 stable, but any version 3 will do. And essentially what we're going to be doing is we're going to be able to walk across walls. Now I'm actually recording this for like the 4th or 5th time because this is kind of a nuanced topic and I didn't want anyone to get lost. And I really want to make this a high quality video. I'll just get into the explanation of how you can make something like this and then we'll actually get to coding it. Let's hop straight into Paint. So let's say we have a room over here, right? Let's just say it looks like a bear for some reason, and this is our red circle player, okay? This red circle represents our player, and what are we going to be doing with the player? Well, we're basically, in our game scene, we're going to be saying to the player, you have a bunch of rays sticking out of you, ray casts. I don't know what the equivalent is for Unity, but whatever the equivalent is, we're basically going to be getting a bunch of ray casts out, and in the ray cast, there's a special function called get normal, or get collision normal. So what is a normal? So if I have this wall over here, the normal of this wall would be this way. If I had this wall over here, then the normal would be over here, kind of like this instead, or it would be like kind of like that. But essentially, it's 90 degrees or perpendicular to the surface it's on. So the normal for this one would be over here. It's kind of like 90 degrees upwards straight. So what would the normal over here be, or what would the normal for this this raycast colliding with the floor? It would be like this. What would the normal for this one be? It would be like this. And basically for each raycast that is colliding with the floor, we're getting the normal, and then we're going to average them out. So the average of those four normals would be something like this. And with this up arrow, we're basically saying that, okay, so we know what the normal of the floor is. And the advantage of doing this is that when we go over here to the side, or when we go over here to like a corner, and I can just showcase that real quick. If I go over here to a corner, then I'm able to quickly wrap around and continue walking on it without too much of a problem. As you can see, you can fall off if you go too quickly, but it also allows me to walk on spheres, and it also allows me to walk on cylinders and basically any weird random surface that you might want to make. I mean, as you can see, I'm able to just walk around and run, and of course I fall down because I'm going too fast, but I mean, if you just slow down, then you're not going to fall down too often. And I mean, that's just a interesting feature of the system. I mean, if you go too fast, then the raycasts don't update that quickly and you get an issue with it. But slowing down does mediate the problem, and I will explain other ways that you can go fast and still have that level of stickiness onto the walls, if you will. But back to the explanation. So we have our player over here with the average normal. So how do we get the forward and backwards direction? And actually I was asked on a when I actually posted this little demo to Reddit, as you can see over here, I just posted it, and I got a comment saying, hey, this looks awesome, but I was actually trying to make it myself. Or what did you do? And this is their post. That was my post. This was their post, and they basically said, how do I get to traverse a spherical or curved floor? Which is a perfectly normal, like not normal, but it is an interesting question. And you can see over here that they tried to visualize it, and they did a good job. I mean, 100% that this idea of, I don't know how visible that white circle and the white background is, but as you can see, they had the idea of getting the player direction correct in both directions, but they didn't draw any normals. But, I mean, I don't know if they know about normals, and I don't know if they're watching it, but whatever. We're just going to go back to the explanation. And as you can see, we have the average normal of the player. Now, like in that visualization that what's the username? That Plonk Master Jones gave, in this visualization, they have the player direction. And that's very important because we're actually going to use that for the cross product. I'll get to the cross product in just 1 second. So as you can see over here, let's just say our player is going in this direction. So we have two vectors, or two arrows. Now remember, this is in 3D. You can do this in 2D, but I think a 3D tutorial would be a lot more helpful for a lot more people because it's just a lot more, everything's just better in 3D. And there was actually a really quick hack that you could do in 2D, but I'm not going to go over that. And it's actually easier to do this in 2D, but you're basically using math hacks at that point, and learning the 3D version is a lot better. So we're going to be taking the cross product between our player's direction, or our supposed direction, and the normal that we get from averaging out all these raycasts. Now, what does that give us, or what does that leave us with? Well, that leaves us with the perpendicular vector. Now, that's really fancy and complicated, so I'm actually going to go over here into Godot, and I have a scene over here called Understanding. And the reason I called it Understanding is because I can't type. And let's say our player is facing in this direction. So we're just looking out into this side, and our average normal is this way. So the only way our average normal could be up in this way, or facing this direction upwards, would be if we were standing on some sort of like, let's just get a random cube over here. If we were standing on the cube and the cube was kind of tilted like this, then that's how we would be able to get our normal. And of course, I'm going to move the player direction up because the player obviously has to be standing on the cube. Now, let's say we take the cross product between this vector and this vector over here. What will that give us? And that's a totally valid question. I just want to make sure that everything on this diagram is totally correct. And as you can see over here, we have two vectors. What will the cross product give us? The cross product would give us the vector that is perpendicular to both of them. And I keep saying perpendicular, and if you don't know what that means, I highly suggest you go on Google. Literally, I'm not using DuckDuckGo, but Google. Just go to Google and search up vector con academy. That's all you have to Google, and you'll be taken to this amazing, fabulous website, which I have used quite a lot, and you could go learn about vectors and go watch all of these. I mean, if you really wanted to learn about vectors and get into game development, 3D game development, I highly suggest you go learn about vectors. And if I go over here and search a vector con academy perpendicular lines, and look, you can see perpendicular lines from equations, and they'll explain it much better than I can because I am not qualified to do this, but at the same time, I still do it. And basically, perpendicular allows us to get a vector that is 90 degrees from this one, 90 degrees from this one. So as you can see over here, that's 90 degrees like this. And we're going to get another vector that is 90 degrees over here. So as you can see, it's 90 degrees like this. And we basically have a direction on the right. And we can move our player now because imagine if these two were hidden, right? We just hide these arrows. How are we going to even know which direction to move in? I mean, it's not like the player is facing in this direction, and we could use that, but we also have to take into account the rotation of whatever surface we're on. And remember, that could be an arbitrary rotation. If you don't know what arbitrary means, it basically means it could be a random rotation, and we have no clue what it could be. And we have to account for all of them. We use the direction the player is looking, and then we take the cross product of them, and we get this new direction that allows us to move our player. And that, as you can see, when I go into the code real quick, you can see that's exactly what I did. I said the direction of going forward is going to be average normal, which is the purple arrow. Ignore the script. Is the purple arrow. Okay, average normal is the purple arrow. We're going to cross it, take the cross product, which means getting a new vector that is perpendicular to both. We're going to take our average normal, cross it with our forward direction, which is this arrow over here. We're going to take the forward direction and cross it. And then we're going to normalize it, obviously, which just means we will return its length, scale to unit length, which means length of 1, essentially. And then we're going to be rotating it by the average normal, dot normalize, negative pi over 2. The reason we have to do that is because if I don't do that, you can see what happens is that if I do that, right now I'm clicking W, like W to move forward. And as you can see, I'm moving 90 degrees left of where I want to move. So obviously that prompts a question, how can I fix that? Well, we can rotate our vector along the axis of the average normal, and we're just going to rotate it by 90 degrees. And in radians, a fancy way of doing angles, we're going to be rotating it by negative pi halves. And if I just save the script and like just continue running the scene, as you can see, I'm right now clicking W. There's no way for you to see it. I mean, I'm not recording my camera, I'm not recording my keyboard or anything, but you just have to believe me, I'm clicking W right now and I'm moving forward. So that's like the bee's knees of how to do it. I mean, there's nothing much else to it. Essentially, that's how the basis is down, and this took me 3 weeks to understand because I was kind of dumb, and it took me a long time to actually put this together. As you can see, I have 2 failed attempts that did not work, and I had like some crazy, I was using some crazy math, and I really didn't understand what I was doing until I actually went back and watched these Khan Academy tutorials and videos on a different account. As you can see, this is a different account that I use. This is a totally different account, and I did watch some of them. I mean, I'm not trying to say I watched all of them, but I did watch some of them. As you can see, I did watch that. It's not like I clicked on them and then clicked out. This is my personal account in for Bigfoot that I use for everything. As you can see, I use this account for actually learning myself. I mean, this is not something I do for no reason. This is actually something I do, although I am questionably active on it, but that's besides the point. As you can see over here, this one did not work. This one did not work. Now we're going to, after solid 30 minutes of recording, we're going to hop straight into actually how we could build something like this. Okay, so let's say we have our player, right? We're going to obviously attach a collision shape. Don't look over here on the left, look over here. We're going to attach a collision shape. We're going to attach a spatial node of just a head. We're going to then attach a camera onto that spatial node, so it looks something like this. we're going to put a position 3D, not over here, but over here in the front, somewhere over here, far away from the player, just in front of the camera. So the camera's facing this direction. So right now the camera is facing this direction, and we just want this position 3D to be in front. As you can see, I just changed the negative z-axis. I just made the z value negative. That's all you have to do. And then I put a mesh instance over it just because I wanted to see where it was. That's the only reason I did. And then we have a checker, which is just an area 3D, or an area essentially, which will tell us where we are, like what body we collided with. As you can see, it's just slightly bigger than the, or is it? As you can see, we just want to make it slightly bigger than the actual collision shape of the player, because that's how we'll be able to detect what body we were on and call some special functions with that if you want to do that. And then we have our ray folder. And now the ray folder is a bit spiky, and I will be going over this because it is probably the meat and potatoes of this entire tutorial. As you can see, it's kind of hard to like look at from the side, so I'm just going to go like this to my default environment, make the ambience black, or I'm going to change the background to be black. And as you can see, it is basically a mess. Now I'm going to deconstruct it. Give me 1 second. I'm going to break it apart piece by piece and explain every single thing that's in it. Okay, so I took away those 2 lines. Okay, so after taking away those straight lines, which I will come back to, which we had 1, 2, 3, 4, 5 of, we can see that we basically have a very simple structure of raycast pointing out in all directions. Now, there are better ways to do this, but I found that having a couple very specific raycasts pointing in all directions, kind of like this. So we have obviously our forward ray, which detects the forward position. As you can remember, I took this ray folder. I basically took it from, not like that, but I went like this to the ray folder. I basically dragged it out from the center of the player. And you can remember that this is the forward direction. Anything facing this direction is the forward direction. And as you can see, we have a forward ray, which goes in forward basically. And we have a backwards ray. We have a right ray. We have everything. But essentially, if you want to get the bare bones down, all you need is this. All you really need is just a group of rays that are kind of like in a cross formation, because kind of like you have one over here on left and right and backwards and forwards. And mind you that these are actually separate rays. As you can see, when I keep deconstructing it, you can see that we actually have separate rays. This one is just joined with that one. As you can see, we have the backwards. No, we have forwards, backwards, left, right, up, and down. And we have these 6 rays. But if you want to be able to crawl across multiple surfaces, which I'm assuming you want to, or if you want to crawl around spheres smoothly or rounded objects smoothly, you have to make sure you have multiple rays and kind of make something like this. As you can see, of course, the code will be in the description, like the entire project will be in the description. And as you can see, we basically have all these values over here, which explain how you can get something like this. But this essentially allows us to get access to our surroundings. And it's very similar to these orange arrows over here. That's basically what I'm trying to drive at, if I wasn't being too clear. Very sorry, though. Very sorry if I wasn't being clear, but we're basically trying to get something very similar to what I drew over here. A bunch of rays sticking out of the player so we can get the average normal. So it's easier for us to climb on curved surfaces. Now that we have the rays and the actual idea out of the way of how we're going to be controlling the player, and as you can see, if I run the scene right now, it's very, very bright. Wow, that is extremely bright. Oh, I'm on a curved surface at the moment. Where am I? Hello? Oh, okay. I lost my bearings there for a second. But as you can see, everything is still working, although it is extremely bright. And after just playing around with the colors, I just got back to what I originally had in. But as you can see, the reason we had to have multiple rays, and the reason we had to have, in specific, rays like these ones over here, the reason we had to have rays that were kind of like pointing off from the side of the player into the opposite direction is because if you think about where that ray is right now, if I just rerun the scene because I know moving things like that hurts. If you think about it right now, one of these rays, a ray like this one right now, might be actually pointing on this surface, and that's allowing us to walk on these corners. And it's actually what makes the entire thing possible. And now you can see over there, I just fell off. The reason I fell off is because I was actually, because I don't have a lot of these rays. I mean, this is just the bare minimum that you need, kind of. You could put more, you could put less, depending on your level design and arena types. But essentially, I found that a number like this works perfectly fine, like around like 20-30 rays pointing out in evenly spaced distribution around the player works perfectly fine for crawling around walls, and especially spheres if you want to do something like that. As you can see, I'm perfectly able, just by holding down the W key, to run around these spheres, and everything works perfectly fine. and random jagged curved surfaces. Everything works perfectly fine. I'm able to run across of it, and as you can see, I'm able to grab onto this and run across it as well. As you can see over here, we have gravity as a vector. Usually in third person, or not third person, but 3D FPS tutorials, you'll see gravity as a number. That's because our gravity changes depending on the surface we're on. Our jump velocity or jump vector is also a vector because we have to change which direction we're jumping. Average normal, we have a mouse sensitivity, speed, which is how fast we're moving, velocity variable, that's just I mean, you could define it elsewhere as well, but I just like defining it up here. We have a jump number, so how many jumps have we done so far? We don't need mouse sense multi. I don't know why we have it. We have max jump amount, which is how many maximum jumps we can do. And of course, 10 is an absurd number, but that's for testing purposes. We have extra velocity, if in case you want to do a dash mechanic or some sort of grapple hook mechanic, which I'll be making a tutorial about sooner or later. We have the up direction or the average normal. We have the jump vectors, which is basically y speed in my previous tutorials, or our y velocity, or the velocity that we will be moving up and down with, or if we are on a wall of some sort, then we'll be moving up, like our jump velocity will be able to dictate the movement across different surfaces. It's imperative that you do it in its own sort of vector variable, because that will help with control later on. And we have our body on, which is what the area will be actually setting, and that's why we have the area there. It's not there for no reason. So obviously we're going to start off this script by just going to the ready function and setting the mouse mode to input mouse mode captured. We're going to connect the checker signal, or from the checker object, which is just the area that is going to be checking our body's like our player's collisions with surfaces. We're basically going to be connecting the bodyEntered signal to ourselves and calling the function bodyEntered. In the bodyEntered function, we're basically going to be saying if the body, like if there's a body and the body is not equal to body on, then we're going to be saying that if that body is also a static body, then we're going to set body on equal to body. Now this is kind of confusing, but it basically says if we entered like a floor or a wall that is not this variable, set it equal to that. Set it equal to body on. And if you want to, you could do this. Nothing's stopping you by doing this. Absolutely normal. And basically that's what we have. We're basically checking if we are on a body that's new, and we're going to be setting that variable over here. And then we're going to be setting our jump vectors equal to vector 3.0. And remember I said that's kind of like our y speed, or the speed associated with how we're going to be moving around on surfaces, like up and down wise. So of course when I mean up and down on a surface, like this means up and this means down. Up and down means motion like this. On this surface, up and down means this. So it's relative to each surface, but let's just assume up and down means kind of something like that, depending on the surface we're going to. And of course that relates to the normal. So we're going to be setting our jump vectors equal to vector 3.0 because we do not want to be like, let's imagine if we were jumping from this surface to this surface. Our jump vectors are basically pushing us in this direction, and they're going to be continuously pushing us in this direction unless once we once we hit this floor, we get rid of this and we tell it to stop doing this. So we basically go back to something like this, and we're now able to reset our jump, and we're able to jump in any direction we want from going forward. In our input function, we're basically going to be saying, and I'm just going to move this down. In our input function, we're basically going to be saying head/camera.rotation.x focuses how we can move our mouse up and down to look up and down essentially, and head.rotation.y plus equals event.relative focuses how we can move left and right. And now if we run the scene currently, you see that I'm able to move left, right, up, down, no problem, but I cannot move because we have not put that logic in yet. Here's where the meat and potatoes of this entire tutorial come in. In this physics process function, we're going to be getting our speed times get direction, and we're going to be doing something with check raise. We're going to be making both of these functions because it's just a lot easier if we break our code down into functions. Okay, so just going ahead and making these functions, as you can see, we have a check raise function that doesn't return anything, and we have our get direction function which returns a vector 3, but it's not doing anything at the moment because this vector 3 is a value of null or 0, or actually it's a vector 3.0 basically. But we're basically not moving, but we're going to be going to the check raise function because there's more stuff here. In our check raise function, we're basically going to be saying, make a variable called average normal, which is different than the average normal up here because this is a global variable that any function can access, but this is a special variable that only we can access, and it just helps us break down the code a little bit nicer. We're going to have amount of rays colliding, or number of rays colliding. It should be number, but it should be number. We have numbers of ray colliding, which is how many rays are actually colliding with the surface. Because remember, over here in this diagram, these orange rays, not all of them are colliding. In fact, most of these aren't. So we have to get a reference to how many rays are actually colliding in order to get our average. We're going to be saying, not amount, but we're going to be saying in this for loop, we're going to be asking for ray and ray folder, which basically is this one over here. We're going to be looping over all of these rays or these ray casts, and we're going to be asking, are you colliding? If r dot is colliding, and I just made a variable over here to help with the TypeScript because, not TypeScript, that's JavaScript, but the type system in Godot, this colon basically sets the type of this variable, and I know each ray, and just a quick note, you don't want to put anything else in here except for ray casts because it's just easier to avoid checking it if we know the only thing in here is going to be raycast. You could, if you really want to, if r dot is colliding and ray is raycast, if you really wanted to do that, you could, but I feel like that just wastes performance. I mean, you don't really have to do that. If you know that the only thing in this and the only thing that will ever be here is raycast, you could basically do a simple for loop and assume it is array. Of course, this is just a game, so it's okay, but if you're doing this in a really like production heavy program, I would highly recommend adding that check-in. Anyway, back on topic, we're going to be asking if that raycast is colliding, and then we're going to say number of rays colliding plus equals 1, because obviously this raycast is colliding, so we're going to add 1 to the number of rays colliding, and then our average normal, which is a variable up here, we're just going to plus equals r.get collision normal. R.get collision normal is raycast.get collision normal. It returns the normal of the intersecting object shape at the collision point, which is just fancy talk for saying this orange raycast, we're going to get its collision point and find the normal. We're going to get this raycast and find its normal. That's basically what it's saying. So let's assume for 1 second that all of our rays are, or at least one of our rays is colliding with a surface and returning a normal. If that is true, if any of these rays is colliding, it will make the average normal equal to something other than vector 3.0. And if that's true, then we're going to obviously make it an average by dividing it by how many things were added to it. Obviously, that's how you take the average. You sum up all of the elements and then you divide by the number of the elements. So sum up all of the rays that are colliding and divide it by the number of rays that collided. I hope that makes sense. And then we're going to set our average normal equal to the average normal variable that we created temporarily, dot normalize. So it's of a scale to unit length. That's really important. It just means made to a length of 1, which helps with our cross product and everything. And then we're going to take our jump vector and we're going to set it equal to the average normal times 50. Why? What does that mean? Jump vector, basically jump vector equal to average normal is essentially saying that if we're our players over here, so let me just make it red. If our player is over here and we want to jump, we want to make sure that we jump like this. We don't want to make it so that we jump like this, because that's essentially what the default scheme is for anyone making an FPS controller. We want to be able to jump like this. Even if we're on a curved surface, we're going to be jumping straight up because that's a common assumption. But if you're on a wall or something, you want to jump to the side or you want to jump like that. So we have to reset our jump vectors to be pointing in that direction. And that's exactly how we do it, by saying take the average normal, which is kind of like this. We're going to multiply by 50. That's pretty straightforward. And then our gravity variable, which is how we're going to be pushed down. Because remember, in most FPS player controllers, you're going to be seeing that the gravity is just pointing downwards. It's going to be pointing downwards regardless of what surface you're on. But in this game or system we're making, we want to make sure gravity is pointing even upwards. Because imagine if you're on the roof of a building. Imagine that if you're on the ceiling of a building, sorry, not roof, ceiling. If you're on the ceiling, then you want gravity to be pointing this way, and you want to be able to jump downwards like this. That's important because then we could set that over here. Now let's take the case that you're jumping in the middle of the air and none of your rays are colliding. Well, we have to employ a special check for that by saying the average normal is just going to be equal to vector 3.up, because let's just assume that when you're jumping like this, right, you don't want to like continue along that trajectory unless you want to. I mean, you could get rid of this, but of course that leads to different results, and I will showcase that. I will come back and showcase this, just a little comment over here for me to come back to. But as you can see, if we're jumping from here to here, then at some point, we're going to want to make sure that our jump variables and gravity and stuff is not pointing us downward. So imagine we jump up from here and go something like this. The gravity at the moment is like this. We don't want to continue jumping like that because that's not what we're going for, of course, because I want to copy the Xenomorph. Okay, so the main inspiration for this movement system actually came from this game I was playing over here. I recorded some clips and like some levels, but basically, as you can see over here, I'm getting 75 FPS. The recording's a bit laggy, very sorry. But as you can see, I'm able to walk along surfaces like I was just able to do over there. I'm able to walk along surfaces. I'm able to take out lights because it's a stealth game. And you can see I'm able to walk along these surfaces and run around them, just like if I was walking on the floor. But just in a moment here, you'll see that I'm walking on this edge over here, and I'm able to walk perfectly fine. And that's super cool. Like, that's such a cool, fun mechanic. I really enjoyed pretending to be the alien, right? Because that's essentially what this video game was. And you can see I'm just standing on the wall over there, and that's really fun and cool and amazing. And I really wanted to make that, and that's where the inspiration of this project kind of came from. But if you want to do something like that, and you continue walking along walls like VVVVV, I believe, then you could do that. But if you want to do something like this, you would have to employ this check, because essentially after we jump off of this wall, our gravity goes back to this, and that's essentially how we can create more realistic player movement systems. I hope that makes sense. And now we're going to go over to our get direction. Now in our get direction function, we're going to be making a variable called the forward direction. What is the forward direction? Well, the forward direction is going to be our position 3D. Remember that position I said to randomly set with the mesh instance? This position minus our head's position. That will get us a vector that is pointing in the direction that we're looking at. If we were going to back to our understanding example, you can basically see that our player head is pointing in this direction, which is very similar to this vector over here that I'm highlighting with my mouse, just this general direction of looking forward. And our average normal is depending on what we're ever standing on, and then we can get the cross product, which is exactly what we're doing over here. We're basically saying that this forward direction variable is going to be equal to position 3D minus where we are right now, dot normalize, and then we're going to be saying if we press up, for example, our direction is going to be equal to the average normal crossed with our forward direction, and then we're going to rotate it depending on whichever way we're looking. And I believe I explained that at the beginning of the video, that if we don't rotate it, we get something we don't want. But of course, we're not going to be moving at the moment if I just click F5 and run the scene, because we have not set up move and slide with our velocity. So if I quickly just toss in a move and slide over here, as you can see, when I move, at the moment, there's no gravity, by the way. If I move, and there's right now no gravity, if I move, let's say I just go like this, I'm able to walk along the surface, right? And if I just go over here like this, and I get rid of the dot rotated, and I control S to save, as you can see, when I click W, which is going forward, I'm walking off to the side, which is not something I want. So we have to rotate it on the axis of our normal, which basically means, sorry to be disorienting for a second, if we rotate it on the axis of our normal, we're going to be saying that instead of going this way, if I control S to save, we're going to be going forward. How does that work? Well, look at what we're doing. Read it word for word. Dot rotated by the average normal dot normalize, comma, negative pi over 2. Well, what does the rotated function take in? It takes in an axis and a very, like a number that we can rotate by. Rotates the vector that is, we're going to be rotating this vector across this axis by this much. Visualized in like a actual like 3D scene, we're going to be rotating this vector by, we're going to be rotating this green vector over here. We're going to be rotating it by like 90 degrees so we can point it in a certain direction. And now the direction we have to point it in is forward. I think that's simple enough. And we can continue this for like forward, backwards, left, and right. And because it's by default pushing us to the left, we don't have to rotate it by any amount, which is pretty nice. There are other ways you could save it. I mean, you could save it like, you could save performance by basically making a variable direction base like this, which is just a vector 3. And instead of typing in everything so clumsily like I did, continuously doing the same computation over and over again, well, you can just say direction is going to be equal to direction base dot rotated by some amount, depending on what we want. And you can continue to do this for the other ones, and direction is going to be equal to direction base for that guy. And for this one, it's going to run like this. And everything is the exact same because we're basically taking out this computation and making it a variable. Okay, I believe that explains the movement system. Now we're going to go over and explain the jumping system and gravity. So it's actually going to be very simple because in our move and slide function, because we have a linear velocity in the up direction, which is partially where I got the inspiration for calling it the up direction, because the up direction is something we can continuously define, Well, we already are continuously defining it by the average normal. So depending on what surface we're walking on, the average normal or the up direction will be continuously redefined, which means is not on floor or is on floor or is on wall or is on roof or is on ceiling, I believe, is going to be continuously defined. Is on ceiling, yeah, is going to be continuously redefined. We have access to, if you are not on the floor, then if you're not on the floor, we want to make sure our jump vectors are going to be added. We're going to make sure our gravity is added to our jump vectors. Else, if you are on the floor, just don't add anything to, or just make sure the jump vectors are equal to vector 3.0. And if we press space, we want to jump. What's jumping though? Jumping is going to be taking our jump vectors, which by the way we're continuously adding to our velocity, and we're just going to be adding our jump vector to our jump vectors. Now, of course, these are very similar, and that's bad planning on my part. But jump vec is what direction are we jumping in, and jump vectors is just a variable that helps us explain the movement system in a vertical fashion. I really hope this makes sense. If not, you can feel free to leave an angry comment. I'll try my best to explain. And of course, after we jump, we want to set our average normal back to facing upwards, which is exactly what I was trying to explain over here. After we jump, we want to make sure our gravity is set back facing downwards to Earth. We don't want it to go like this, unless that's something you want to go. I mean, totally up to you. I mean, if I get rid of this, right? As you can see, when I get rid of it, everything still works the same because of our check employed by our collision over here. But if I get rid of this as well, you can see that when I jump, right, I'm able to it's kind of like, I don't know what the exact word for this is. I mean, I feel like I've seen it in a video game somewhere where like the floor that you're touching currently is the floor that becomes the one that you are ultimately stuck to. Like, for example, if I jump this way, right, it's kind of like I have gravity on this one. I've seen this somewhere. I don't know where to explain it, where I saw it from. I've surely seen it in some sort of movie or video game, but essentially that the direction that I'm looking at, it becomes a new direction. So as you can see, if I jump from here, it's kind of scary because like I'm jumping from it should logically make me fall down, right? Like, let's say I'm just on this ceiling over here and I jump, then it's kind of like I'm jumping back and I have gravity. But as soon as I turn this, and I mean, if I turn either or on, I mean, if I turn this off, right, and turn this one on, as you can see when I jump, my jump vectors are set back to 0. And if you really want to, I just defined a couple of things here in the input map over here. Just defined R and shift and space. That's where I defined all of these things, which allows me to get these key presses. And shift is something I just use for sprinting. As you can see over here, if I just click shift, of course I have to rerun the scene, I think, if I make a change like that. If I click shift, I'm able to crouch. I'm sorry if I said sprint. I'm not sure if I did. But if I did say sprint, I meant shift to crouch and slow down. And as you can see over here, everything's working perfectly fine. I'm able to just walk along any surface, and it's pretty cool. So if you wanted to make something like that, as I know Plonk Master Jones did, I'm happy if you take away and learn something. I mean, I hope I explained anything. I hope I explained everything logically and it made sense. If I did not, feel free to leave me a comment saying I explained it horribly, and I'll try my best to explain it in words. I hope I explained it briefly. I'll upload like a extra part of stuff I tried to explain and just extra clips to help consolidate this concept, because this is kind of a hard concept to put your head around, because this is 3D vector math, right? I don't want to get like too esoteric, but that's pretty interesting, complex topic which deserves its own attention, and it's far too great that I could cover in a small YouTube video. But I mean, like, if you search up cross product animation and just watch something that explains the cross product, as you can see from this preview, the cross product is the C vector as over there. As you can see, it's just shrinking depending on where you're looking. I mean, this video is really amazing. I mean, I just searched up cross product animation. I was able to get it, so you should be able to do it as well. I mean, anything here, just search up cross product, 3D vector math. You'll be able to figure this stuff out by yourself and hopefully make a really cool movement system like I did. I'm really sorry if things I explained did not make 100% sense. If something didn't make sense and you were actually talking to me in real life, I would be able to understand what you did not understand, and I would be able to explain it better. But without that, I'm not really able to know what you did not understand. So if something didn't make sense, please feel free to leave a comment, because I'll try my best to respond to them. And basically, you can make something like this. As you can see, I'm able to walk along these spheres, head back, walk along the side of the spheres, which I think is pretty cool. I'm able to shift across. I'm able to like slowly crouch across these surfaces of these cubes, walk along these surfaces, and it's a pretty cool spy stealth mechanic, I guess. And that's where I'm going to leave this tutorial. I mean, I hope I really hope this helped, and have an amazing day. I just want to comment on a couple of things. As you can see over here, if I'm walking slowly along the edges, I do get stuck. Unfortunately, I have no way to solve this, but at the same time, with such like diverse like movement mechanics or something like this free, there are bound to be issues. I'm not trying to use that as an excuse, but I'm just saying that this is still a work in progress for me as well, as I am still new to 3D math topics myself and Godot itself and programming. So of course, you shouldn't really trust me to make a movement system, but at the same time, it works for a majority, like 99% of cases. But I'm just saying that there are like a couple of issues to be aware of, and that's just one issue I found. The other issue I found is that if you're on a ceiling or a roof, essentially, or on the upside down part of a roof, walking like this is fine. Like walking like this is totally fine. But as you can see, it looks a little weird. So you might want to nudge the player to move like this. As you can see, when I move my mouse left, I move right. When I move my mouse right, I move left. There are ways to fix it by multiplying this by -1. So if I just do something like this, so I just quickly put a negative over here, as I can see. Now I'm moving my mouse left, I move left. But over here, now it becomes really hard for me to control because I expected to move my mouse left, and I'm moving right. Now I expect to move my mouse right. I should look right, but I'm moving left. And this hack I found works well enough. I mean, as you can see, I'm on a surface. If I'm just like telling you that I'm able to look properly, like right now, I think I'm looking in the proper directions. I'm just making sure everything's working. I'm able to look around. But if I go over here on the sphere, right, as you can see, that was a little bit weird. But now I'm getting into some weird territory. But on flat surfaces at the bottom-ish, it's working perfectly fine. I'm able to look around. But just a little disorienting when walking around spheres because the way the camera system shifts and turns. As you can see, that was just a small issue you have when you look straight ahead. That's a notable issue because right now the cross product between the average normal and our forward direction is exactly the same. So it's basically looping us around in circles. As you can see, if I just increase this a little bit, it basically just finds and goes to the position where it jiggles like this. I mean, there are a couple workarounds, which is to continuously rotate the camera itself, which I'm working on. But I mean, other than those couple bugs, I mean, the entire system works perfectly fine. And I feel like a bug like this is I mean, it's not a game-breaking bug. I mean, yeah, it is mildly infuriating that you can't walk forwards when you're over here. But at the same time, I mean, which direction is forward? Like, is forwards this way, or is forwards this way? I mean, when you're looking straight ahead like this, it's not completely obvious, which I mean makes sense mathematically and makes sense in the game. So it's kind of like a feature. I mean, I am kind of trying to protect this, but at the same time, I am quite tired after working. I am quite tired of working on this for a solid like 2-3 weeks. So yeah, that's any notable bugs. And of course, if you have any comments, feel free to leave them in the description. And of course, as you can see, that's how tired I am. And of course, if you have any comments or questions, feel free to leave them in the comment section. I'll be happy to answer them.